The cosmos has always intrigued humanity, offering more questions than answers, and every new discovery only seems to deepen the mystery. But now, in the age of modern telescopes like the James Webb Space Telescope, we find ourselves on the edge of a potential paradigm shift in our understanding of the universe. What we once thought we knew is being called into question, and even Nobel laureates like Adam Rees, whose research shaped our understanding of dark energy and the accelerating expansion of the universe, find themselves puzzled by the new revelations coming from the farthest reaches of space. For decades, cosmology has relied on certain key concepts to explain the workings of the universe, concepts like the Big Bang, the expansion of the universe, and the distribution of galaxies. These ideas were formulated based on observations and mathematical models, and while they have been remarkably successful in explaining many aspects of the universe, they may now be reaching their limits. As the James Webb Space Telescope, with its unprecedented sensitivity and ability to peer deeper into the universe than any telescope before it, continues to send back stunning images and data, the very foundation of our cosmological models is being tested like never before. One of the most perplexing puzzles to emerge is the so-called Hubble Tension, a discrepancy in the measurement of the Hubble Constant, the number that describes the rate at which the universe is expanding. The story of the Hubble Tension is not just a matter of differing numbers, it points to a deeper problem in our understanding of the universe. How can two different methods of measuring the universe's expansion give such different results? What does this mean for our understanding of cosmic history and the forces that govern the universe? These questions are at the heart of a mystery that has been baffling scientists for years, and it's only now, with the help of the James Webb Space Telescope, that we may be starting to uncover the answers. The history of the Hubble tension begins with Edwin Hubble, the American astronomer who, in the early 20th century, discovered that the universe is expanding. He observed that galaxies are moving away from us, and the farther a galaxy is, the faster it is receding. This led to the formulation of the Hubble law, which describes the relationship between the distance to a galaxy and its velocity of recession. This simple yet profound observation laid the foundation for modern cosmology and led to the formulation of the Hubble constant. The Hubble constant is a number that tells us the rate at which the universe is expanding. The problem, however, is that this constant has never been a single, universally agreed upon value. There are two primary methods for determining the Hubble constant. One method uses the cosmic microwave background, CMB, radiation, the faint afterglow of the Big Bang. This radiation is a snapshot of the universe when it was only about 380,000 years old, and it provides us with a way to measure the expansion of the universe in its early stages. When scientists use this method, they arrive at a value of around 67 kilometers per second per megaparsec for the Hubble constant. A megaparsec is a unit of distance, about 3.26 million light-years, and this value has been supported by measurements made using the CMB data collected by observatories like the Planck satellite. On the other hand, the second method for measuring the Hubble constant involves observing more local galaxies, specifically using Cepheid variables, stars that pulse in a regular pattern. These stars are known to have a direct relationship between their brightness and their pulsation period, which allows astronomers to calculate their distances. By measuring the distance to Cepheid variables in nearby galaxies and observing their velocities, scientists can calculate the rate of expansion of the universe in the local cosmos. This method, which has been refined over the years by astronomers like Adam Rees and his team, gives a much higher value for the Hubble constant, around 73 kilometers per second per megaparsec. So, we have two different numbers for the same quantity, the rate at which the universe is expanding. This is the Hubble tension, and it represents a major puzzle in modern cosmology. At first, many scientists thought the discrepancy might be due to some kind of error in the measurements or assumptions made in the calculations. But as the data from both methods became more precise, the gap between the two values only seemed to grow, and it became clear that the Hubble tension was not just a simple measurement error. It pointed to a much deeper problem. This is where the James Webb Space Telescope comes into play. Launched in 2021, the JWST is the most powerful space telescope ever built. It is equipped with a suite of instruments that allow it to observe the universe in infrared light, which is essential for studying distant objects that are too faint or too distant to be seen in visible light. The JWST is capable of observing galaxies that are billions of light-years away, providing us with a glimpse of the universe as it was in its early stages. Given its remarkable capabilities, many scientists, including Adam Rees, hope that the JWST might help solve the Hubble tension by providing more accurate measurements of the Hubble constant. In 2023, Rees and his team used the JWST to observe galaxies in the distant universe and attempt to resolve the discrepancy in the Hubble constant. They were looking for any signs of measurement errors that might explain the differences between the two methods. What they found was surprising. There were no errors in the data from the Hubble Space Telescope, which had provided the lower value of the Hubble constant. The data from the JWST confirmed the high value of 73 km per second per megaparsec. In other words, the Hubble tension still exists, and it is as mysterious as ever. So, what does this mean for our understanding of the universe? It suggests that there is something fundamental about the universe that we are not yet understanding. It raises the possibility that our current models of cosmology, which are based on Einstein's theory of general relativity and the standard model of particle physics, may be incomplete. Perhaps the discrepancy in the expansion rate is a sign that there is something about the nature of gravity, or the distribution of matter, that we don't fully understand. Some scientists have suggested that the problem might lie in the way we measure distances in the universe, particularly in the more distant reaches of space. In fact, one potential explanation for the Hubble tension comes from the idea of cosmic bubbles. These are regions of space where the density of matter is lower than average, surrounded by regions of higher density. Some scientists, including those from the University of Bonn and the University of St. Andrews, have proposed that our galaxy resides in a bubble-like region of space, which could explain why we're observing galaxies moving away from us faster than expected. The gravitational forces from the dense regions surrounding the bubble would pull galaxies towards the edge of the bubble, causing them to move away from us faster than we would expect based on current models. While this idea is intriguing, it raises further questions about the distribution of matter in the universe and the nature of gravity itself. The concept of cosmic bubbles challenges the standard model of cosmology, which assumes that matter is evenly distributed throughout the universe. If these bubbles really exist, they would require us to rethink our understanding of the universe's large-scale structure. More importantly, it would imply that our theories of gravity, based on Einstein's general relativity, might need to be modified to account for these irregularities. In fact, this idea is reminiscent of a theory proposed by Israeli physicist Mordechai Milgram in the 1980s, modified Newtonian dynamics, MOND. MOND suggests that gravity behaves differently at large scales than we currently understand, and it has been successful in explaining some of the anomalies observed in galaxies, such as the rotation curves of spiral galaxies. However, MOND has not been widely accepted by the scientific community, and it remains on the fringes of cosmological theory. If the Hubble tension is indeed related to cosmic bubbles and the nature of gravity, it could have profound implications for our understanding of the universe. It would mean that the laws of physics, as we currently understand them, may need to be revised or extended to account for these new discoveries. And this, in turn, could lead to a re-evaluation of some of the most fundamental questions in cosmology. How did the universe begin? What is the true nature of dark matter and dark energy? What is the future of the cosmos? These are questions that have been at the heart of cosmology for decades, but the new discoveries made by the JWST are forcing us to reconsider the answers. One of the most exciting and puzzling discoveries made by the James Webb Space Telescope has been the observation of ancient galaxies that seem to defy our current understanding of galaxy formation. These galaxies, which formed just a few 100 million years after the Big Bang, are much more massive and mature than they should be according to current models of galaxy evolution. Some of these galaxies, such as the galaxy known as Jade's GSZ 140, are already tens of billions of times the mass of the Sun, far larger than any galaxy we thought could have formed so early in the history of the universe. These findings are challenging the conventional wisdom that galaxies evolve slowly over time, building up their mass gradually through the merger of smaller galaxies and the accretion of gas and dust. The presence of these early, massive galaxies raises a host of questions. How could they have formed so quickly? Where did all the matter come from? Current models of galaxy formation suggest that large galaxies should take billions of years to form, but the galaxies observed by the JWST appear to have reached their enormous size in just a few 100 million years. Some scientists have even suggested that the early universe may have been far more efficient at producing galaxies than we previously thought, with conditions that allowed galaxies to grow much more quickly than our models predict. These discoveries have led some scientists to question whether we need to revise our entire understanding of galaxy formation and evolution. Perhaps the early universe was more densely packed with matter than we realized, allowing galaxies to form more rapidly. Alternatively, the formation of these massive galaxies could be the result of processes that we don't yet fully understand, such as interactions between dark matter and regular matter that lead to faster than expected growth. Whatever the answer turns out to be, it's clear that the conventional theories of galaxy formation are being challenged by these new findings. At the heart of all these discoveries is a fundamental question: are we on the brink of a new understanding of the universe, one that will reshape our theories of cosmology, gravity, and galaxy formation? The Hubble Tension, the strange new galaxies observed by the JWST, and the possibility of cosmic bubbles all suggest that our models of the universe are incomplete. But they also represent an exciting opportunity for discovery, one that could lead to a deeper understanding of the universe and our place within it. As we continue to explore the cosmos with the help of telescopes like the James Webb Space Telescope, it's clear that we are only scratching the surface of what's out there. Every new discovery challenges our assumptions and forces us to rethink the way we view the universe. The future of cosmology is filled with unknowns, but one thing is certain: the journey to understanding the universe is just beginning, and the answers we find will likely be far more surprising and complex than we ever imagined.